Our speaker for today is Federico Mocchetti. He will speak about Weil conjectures. And Fede, the stage is yours.
Thank you, Matteo. Okay, so first of all, I should thank Krishna because in a couple seminars before, he already introduced the statement, so I just wrote it on the blackboard before the beginning. Let's recall what Weil conjectures are about. So let x0 be an algebraic variety over a finite field of Q. So Q will be a power of a prime. With algebraic variety, we mean schemes separated into finite type, but this does not really matter. Which is smooth and projective of dimension d. And we define its zeta function to be this power series in T. And here I use parentheses. So the statement of the Weil conjectures, the statement of the Weil conjectures is divided into three parts. First statement is about rationality. So z of x0t is in fact a rational function, meaning a quotient of polynomials in Q. It satisfies this functional equation. So z of x0 evaluated in 1 over q to the d, q to the dimension t is equal to epsilon q to the d key divided by 2 times t to the key times z of x0t, where epsilon is plus or minus 1 and key is the Euler characteristic of our variety. And finally, the Riemann hypothesis, which gives a more precise statement about the form of our zeta function. In particular, it says that there exist 2d plus 1 polynomials with integral coefficients such that the zeta function is expressed as this fraction. So odd degree, odd index polynomials at the numerators divided by the product of the even index polynomial. Moreover, these integral polynomials have a very specific form. In particular, the 0th one is 1 minus t. The 2dth one is 1 minus, well, here it's a bit confusing, but it is 1 minus q to the d times t. And all the others in between have this form. So if we express them as this polynomial, here I should write more properly as a product in polynomials with coefficients in C, so we find all of their roots, then the roots have this absolute value. And this is essentially the statement of the Weil conjectures. These statements were proposed by Weil in 1949, but I mean, their history before Weil stated this conjecture and after the statement until the proof is quite long. So let me recall partially this history. One of the first results is about the proof of these Weil conjectures for the case of elliptic curves, and this was done by Hasse between 1934 and 1936. Then, as I said, Weil proposed the conjecture in 1949, and in the very same paper, he proved it for a specific kind of varieties, namely those that are called diagonal hypersurfaces, whatever they are. Then the rationality of the zeta function was established by Dwork in 1960 using some p-adic functional analysis technique. Then there was the advent of Elliptic cohomology developed by Artin, Grothendieck, and others. And this gave another, one could say better, proof of again rationality, and then also of the functional equation. And finally, Riemann hypothesis was first proven by Deligne in 1973. And then his proof was generalized to a larger class of functions, of varieties, in 1980, if I'm not wrong. So what will I talk about today? Today, I would first like to present you the proof of Weil conjectures for elliptic curves, as this is a seminar about elliptic curves. And then I want to do something a bit more ambitious, namely take one of these three assumptions and prove it. To my personal preferences, I would have chosen something involving cohomology, so something that came after the work of Artin and Grothendieck. And since I want to do something like everybody knows the name, I chose Riemann hypothesis. Unluckily, the proof revealed itself way too long, so I'm not going to prove the Riemann hypothesis, but I'm just going to reduce it to a couple of inequalities. That's the aim for today. So let's go on without losing any more time, and let's think of what the statement of Weil conjectures is for elliptic curves. So let E over FQ be an elliptic curve. Then there exists an element in Z such that its zeta function is expressed like this. So 1 minus AT plus QT squared divided by 1 minus T times 1 minus QT. And if we factor this, the numerator in particular, in C as 1 minus alpha T times 1 minus beta T, we have that the modulus of alpha is equal to the modulus of beta, which is the square root of Q. And finally, zeta of ET satisfies this functional equation, which is exactly that one if you plug in like the Euler characteristic of an elliptic curve. And then, well, in this case, we have epsilon equals to +1. Okay, so how does one prove this statement? Well, let me erase the blackboard. The first fact that I would like to recall you, the first ingredient to the proof, is given by some results on M torsion M an integer for an elliptic curve. So let M be a natural number, and we define the M torsion subgroup of our elliptic curve to be the set of points of the elliptic curve such that M times the point is equal to the neutral element. And this we call the M torsion subgroup. Okay, well, we say that E over K is an elliptic curve. We have a very nice result about what this M torsion subgroup looks like. Namely, if the characteristic of the field over which the elliptic curve is defined is equal to 0, or the characteristic of the base field does not divide M, then the M torsion subgroup looks like Z over MZ times Z over MZ. Very nice. In fact, this result has a statement also in the remaining case, in which the elliptic, I mean, you can explicit the form of this subgroup almost in any case. So, a very powerful result. Knowing this, we can define what is the L-adic Tate module of our elliptic curve. So, definition, let L be a prime. Number. The L-adic Tate module of the elliptic curve E is the limit over the positive integers of E L to the n, where the maps we use in this limit are given by L to the n plus 1 to E to the L to the n So we take a class here, we do it, we multiply it by L, and then it becomes an L to the n torsion class. From this result, we clearly have that if L is different from the characteristic of K, then the L-adic Tate of E is isomorphic to the p-adic completion of Z times the p-adic completion of Z. Very nice. Okay, last thing I would like to say as introduction about this M torsion stuff of elliptic curve is that if we have an isogeny phi from E1 to E2, and for simplicity, I mean defined over the same field, then we have maps phi, which we might call phi Ln from the L to the n torsion of E1 to the L to the n torsion of E2. Meaning that since this phi has to respect the group structure, an L to the n torsion element will be sent to an L to the n torsion element. And since these maps are nice and compatible one to another and whatever you may like, we get a map phi L from the L Tate of E1 to the L Tate of E2. In particular, This means that we have a representation from the endomorphisms of one elliptic curve to the endomorphisms of its étale. Now, by looking at the structure of the étale, this means that we can associate to an endomorphism of an elliptic curve 2 by 2 matrix with coefficients in, well, more generally we could say in QL, but probably ZL is enough. And so in particular, we pass from phi to phi L, and we can associate to phi L quantities like the determinant of phi L and the trace of phi L. Okay, nice. This association is in fact universal in some sense. Why am I saying this? We have this result that says that the determinant of phi L is equal to the degree of phi, and the trace of phi L is equal to 1 plus the degree of phi minus the degree of 1 minus phi. Well, in fact, the very content is in the first assertion. The second one is just some linear algebra fact. So, what is nice about this proposition is that these two numbers are in fact integers, and they are independent of L. That's why you can think of some universality of these representations. Okay, any questions so far? Okay, so we can move on to the second ingredient, and namely, the second ingredient is given by the Q Frobenius. So, given an elliptic curve over FQ, the Q Frobenius map is just, which we indicate by phi. There are many phis now, but this is the phi, which sends a point of coordinates xy to q to x to the q, y to the q, and this is the Q Frobenius endomorphism. The relevance of the Q Frobenius comes, in fact, from field theory. In particular, if we consider extensions of FQ, the points fixed by the Q Frobenius are the ones that really have coordinates in FQ. And in particular, we can do this for any n. We can, in fact, think of since Q is, in fact, equal to some p to the n, to a prime power. The Q Frobeni are maps that help to distinguish which point belong to which extension of FP or of FQ, as one might think. Yeah, well, maybe let me write it. X is an element of FQ if and only if p of x is equal to x. is the really relevance of the Q Frobenius and why it is a such important map for finite fields. Okay, let's state a theorem. First theorem of today. And this theorem goes like this. So let A to be the quantity Q plus 1 minus the cardinality, or let's keep a more consistent notation, the cardinality of the FQ points of the elliptic curve. Then, first statement, the polynomial t squared minus at plus q factors as t minus alpha, t minus beta over the complex numbers. And we have that alpha and beta are of equal module square root of q. Moreover, for every n bigger than or equal to 1, the cardinality of points with coordinates in the q to the n extension of fq is equal to q to the n plus 1 minus alpha to the n minus beta to the n. So this in particular is a natural number. The second assertion of this theorem is that the Q Frobenius satisfies this functional equation phi squared minus a phi plus q equal to 0 in endomorphisms of the elliptic curve. Okay. Maybe let me say just a couple of words about the proof of this result. The first part of this theorem comes from the fact that due to some, I would say, like magic about elliptic curves, one can write the determinant of t minus L to be equal to t squared minus the trace. Well, this is not really magic about elliptic curves, it is just linear algebra. PL t plus the determinant of PL. This is the magic about elliptic curves, and this is equal to t squared minus at plus q. Okay, then what does one do? One evaluates these on rational numbers and finds out that the determinant of m over n minus phi L is equal to the determinant of m minus n phi divided by n squared, which is equal, phi L, which is equal by this identity to the degree of m minus n phi divided by n squared, and this is greater than or equal to 0. Which means that this polynomial has, well, for sure it has real coefficients, but it has complex conjugate roots. So that your roots have the same modules, and since Q is the product of them, their module must be square root of Q. The most interesting part, one might say, is this one, but this follows just really by the fact that what I told you, Q Frobenius to the nth power finds out which point have coordinates in the nth extension of FQ. So the cardinality of E FQ to the n is equal to the degree of 1 minus phi to the n, which will be equal by that identity to the determinant of 1 minus phi L to the n, which will be by some linear algebra 1 minus alpha to the n minus beta to the n plus q to the n. Okay, point B is just K. Hamilton. Which I recall you as the result that says that an endomorphism satisfies its characteristic polynomial. Okay, nice. And this result is really what allows us to prove Weil conjectures for elliptic curves. How do we prove it? Well, we do one thing which we will see a couple more times today. What is this thing? We consider the log of z of e t. I recall that we defined z as the exponential of some series, and that is due to the fact that we want to pass to the product and to pass to a product version of z, and that exponential really helps this. But for really for making computation, one frequently passes to the logarithm of that. By definition, this will be equal to the sum for n going from 1 to plus infinity of the cardinality of E f q to the n, t to the n over n by these. This is just sum for n from 1 to plus infinity of 1 minus alpha to the n minus beta to the n plus q to the n t to the n divided by n. And essentially, I believe that one can prove that for t large enough, for t small enough or large enough. Well, for an enough, a good quantity, a quantity good enough of t's, this thing converges and absolutely, and we can remix terms, etc. But I have not really made any concern about this. But whatever, this can be reassembled into the power series defining 4 logarithms, namely minus logarithm of 1 minus t plus logarithm of 1 minus alpha t plus the logarithm of 1 minus beta t minus the logarithm of 1 minus q t. Then use the properties of logarithms. You can reassemble that into that shape. Well, log equal to log. Then you remove the logs and you obtain this. Then we already know that alpha and beta have the right modulus from the previous theorem. And then the functional equation is just about like plug in qt 1 over qt and verify that thing's solved. Okay, very last assertion of this first part. Why are we calling this the Riemann hypothesis? Maybe the most informed ones will already know, but let's make it more explicit. I mean, probably what most people know about the Riemann hypothesis is that it regards a small zeta function, and that we want this zeta function to have some symmetry like this. And we also want that if zeta of s is zero, that zeta of s is equal to 0 in some places, in particular those which have which have the real part of s equal to 1/2. Well, this is a bit improper, but trust me that this is relevant. We define zeta of s to be the evaluation of our bit zeta at q to the minus s. So, well, I mean, just plug in q to the minus s, and this will be equal to 1 minus a q to the minus s plus q to the plus q times q to the minus 2s over 1 minus q to the minus s times 1 minus q times q to the minus s. I could have avoided writing this, but whatever. Then what do this assertion tell us? Well, the functional equation is immediate that gives this kind of symmetry. And then the assertion on the roots says that zeta of s is equal to 0. In this case, we can put an if and only if, because we have this very precise expression for it. So if and only if the absolute value of, well, not really if and only if, but, well, let's be a bit more precise. If and only if the absolute value of q to the minus s, well, I'm making my life so complicated with implications. So if q to the s is 0, then we have that q to the minus s must have absolute value equal to q to the minus s is equal to square root of q, which means that well, what we wanted, that the real part of s is equal to 1/2. Oh yes, because these are not the roots, these are the inverses of the roots. Yes. Okay. And that's why we call this Riemann hypothesis. Any question? Okay, so maybe it's better we make a break now. Okay, so we can start the second part of the talk, and as I promised you, I would like to talk about the proof of Riemann hypothesis over finite fields by Deligne. Before digging into the technical aspects of the proof, and in particular to the machinery necessary to formulate the proof, I would like to show you this graph from this article by Nicholas Katz, which illustrates quite clearly the people involved in the formulation and then proof of this Riemann hypothesis over finite fields. and all the various topics, theorems, well, some of them, that were involved in this history. So passing from analysis to geometry, then monodromy, topology shifts. As you see, many important names, many different like interesting theorems, like Hard-Lefschetz, or I mean, choose your favorite. Okay, this is done, and let's go back to the blackboard. Okay, so how can one possibly tackle the problem of, I mean, this Riemann hypothesis for algebraic surfaces? We need a quite powerful bazooka to address such a general problem. And in particular, this bazooka is a cohomology theory. And we will define it as a check cohomology theory, but the standard check cohomology, so the one in which you consider open subset and then complexes of open subset, we will revise this in a minute, is not the right thing to do. Is not powerful enough if we can like measure power of cohomology theories. I mean, in particular, it fails to give a factorization of the zeta function in the rational numbers. The conceptual problem behind it is that Zariski topology in this setting is insensible to field extensions. I'm being very vague, but in some sense, we need some cohomology that behaves well when we base change our field, when we add roots to polynomials. And this cohomology is the étale cohomology. How we define the étale cohomology? Well, the first ingredient are étale maps. Which I recall you, but you can forget it, that étale maps are flat unramified maps. What you must remember is that if we have a separable field extension, k prime over k, and we have x to spec k, a scheme over k, then the map induced by the field extension from, I mean, the base change to x is étale. So we're happy because we can add roots to polynomials. Fine. Okay. Now that we perfectly know what étale maps are, we define the Grothendieck topology generated by étale maps. It is called Grothendieck topology because if you remember the history I gave at the beginning, it was introduced in the 1960s by Grothendieck to solve the second point of, but to reprove the first point and solve the second point of Weil conjectures. What is the Grothendieck topology? Well, when we have a topology, we must define what are the open subsets and what are the unions of open subset and what are the finite intersections of open subset. So, open subset of a scheme X will be an étale map from some xi to x, whatever xi, given that the map is étale. If we want to perform a union of an arbitrarily indexed set, so of étale maps of this form, then this will be given by the canonical, maybe use J. The canonical map from the disjoint union of the xj to x. And spoiler alert, it is still étale. Well, if we want to intersect two étale maps, well, we just have to take the fiber product this will be F1 and this will be F2, and the intersection is the diagonal. I mean, since it is commutative, either way you follow the path, it gives the same result. And again, spoiler alert, it is still étale. Fine, we have a topology. Wonderful. And we define a check cohomology. Check. So now this in fact holds with respect to any cohomology defined in the check way. So you choose a covering of x u of x by open sets. And given a sheaf, in fact, any sheaf f on x, sheaf, one needs to perform operations, so on bet it's sheaf of abelian groups would be fine, but I mean, you have much freedom in the category. We define the ith check cohomology group of x of the covering U with respect to the sheaf F to be the ith cohomology group of this complex, the complex given by these elements, which I'm going to define in a minute. Where the ith element of the complex is given by the product over the multi-indices, like where I is an index on the cover, and we mean by U multi-index I the intersection, like U1 intersect U2, U intersect U3. And the differential of F evaluated at the multi-index I, which will be from I0 to IN plus 1, because it is a cohomology theory, so the index traces will be the sum. I'm using an improper notation, but I hope you'll understand. J belonging to this multi-index I of -1 to the J F of I minus J. So you use j that goes from 0 to n plus 1 minus 1 to the j. F of I minus j is just f evaluated of I, at the multi-index from which you subtract the jth coordinate. Fine. Now we want to kind of universalize with respect to coverings to get a cohomology on X. So we define the check cohomology, well, in fact, the whole cohomology theory. If we have a map of open coverings from U to V in the usual sense, so any open set in U is also an open set in V, then this clearly induces a map from the cohomology theory of U shift F to the cohomology theory of V shift F, because in particular, any element of the complex here will be an element of the complex there, etc. This is kind of standard. And then we define the étale cohomology theory of the space X for the sheaf F to be the colimit, direct colimit in fact, on étale coverings of these safe and sound. Okay. Now, it is standard to require cohomology theories to satisfy. Natural is a kind of forbidden word in this context, but natural properties. And in fact, it was proven by Grothendieck with much more effort than one usually does for cohomology theories defined on open subsets, that étale cohomology respects these properties. And the main reason is that if you compare Zarinsky inclusions, so standard open subsets, with étale maps, well, you have a lot more étale maps than open subsets. And this can cause quite problems, but only apparently, because you have all the nice properties you could desire, at least in the context we want to. So, well, maybe it's better if we erase a blackboard or two, because there are many good properties. So, let X be smooth projective over K with K an algebraically closed field, and let L be prime, L different from the characteristic of K. Then, if D is equal to the dimension of X, then we have that the étale cohomology groups, let's do a nice thing. I'm going to suppress the ET sub-index because we were going to talk only about étale cohomology. So any cohomology will be étale for this talk, please. If D is the dimension of X, then the cohomology groups of X vanish if J is bigger than 2 times the dimension. Very similar to complex, into standard check cohomology over complex manifolds. Finiteness. Each H, J, xql is a finite dimensional QL vector space. Nice. Cohomology is contravariant on the space. But this is not really a special property. I mean, every cohomology is contravariant on the space. So, then we have a trace from the highest non-zero cohomology group to QL, which induces Poincare duality. So, forgive me for not putting the names. So 2D minus I tensor HI to QL. Then we have so many nice properties. We have a Kunet formula. So the nth check cohomology group of a product. Well, Y is just like X. I mean, smooth projective over the same K, algebraically closed. Then this will be isomorphic to the direct sum for J plus I equal to N of HI of X, always with coefficients in QL, tensor HJ of Y. And finally, really the main actor, Lefschetz formula, which apparently can be derived quite easily from the quite easily is a kind of exaggeration, but could be derived from the others, from what I've read, but I'm not totally sure. So let's give her the dignity, her because formula is female in Italian. So given a map F from X to itself with isolated poles, we have this wonderful formula. If we denote by, well, let's just with isolated, of course, fixed points. Plus some extra assumptions, which I'm not stating because they're quite too technical. If L of F is equal to, we denote it by L of F the number of fixed points. So in particular, it is natural number. Then L of F is equal to the sum for I going to from 0 to 2 times the dimension of -1 to the I trace of the action of this map with isolated fixed points on the ith cohomology group itself.
Sorry, Federico. Isolated, what does it mean? Isolated.
Isolated.
Yeah.
I mean, in topological sense.
That's I don't remember. Sorry.
It means that they do not accumulate or they do not form a higher dimensional variety.
Sorry.
And well, spoiler alert. Frobenius discussion F. I'm saying spoiler alert because we will apply Lefschetz formula to the Frobenius endomorphism to get closer to the final inequalities I promised you. Just a brief remark. Since we are assuming projective variety, it will be in particular compact. Closed subspace in compact is compact. In fact, some of these require to pass to the compactly defined the cohomology with compact support. I'm not making the distinction because we are assuming the variety to be projective. So compact and non-compact cohomology is the same, but for the general setting, in particular, if you remember, Poincare duality in the usual setting requires one of the two to be compact support, if I'm not wrong. Whatever. Very easy, very nice in this setting. So, I should fulfill my promise. Let's tackle Riemann hypothesis. So I recall you that our statement, which we will call our H, is that there exists P0, P2D polynomials with integral coefficients such that zeta of x0 t, x0 being algebraic variety, nice, as I said in the beginning, is equal to P1 times P2D minus 1, P0 times P2D. Moreover, we have that P0 is equal to 1 minus T, P2D is equal to 1 minus Q to the D T. And the roots of Pi, the roots as complex numbers in Pi, which we might call alpha ij, have absolute value of alpha ij, modulus of alpha ij, equal to q to the minus I over 2. Why have I introduced you étale cohomology? Because we want to transform this assertion to an assertion on cohomology. Oh, well, let's recall also that zeta of x0 t is defined as the exponential of the series of the number of fq to the n points of our variety times t to the n divided by n. Let's consider what Deligne calls the logarithmic derivative of zeta, which is nothing but t times d over dt of the logarithm of zeta. Okay, so logarithm of zeta just removes the exponential. Then if we take the derivative in t, again, let's not bother about convergence. This will be just t to the n minus 1 times n, so n and t to the n minus 1 cancel, n at the denominator and n at the numerator cancel one another. Then we multiply everything by t, and the t to the n minus 1 becomes again t to the n, so this will be equal to the sum for n going from 1 to infinity of the cardinality of fq to the n points times t to the n. Now, it is a fact that if we consider the logarithmic derivative of this strange function, so it is the determinant of 1 minus f of t of f being some endomorphism acting on a vector space V to the minus 1, well, this will be equal to the sum, the series, in fact, for n bigger than or equal to 1 of the trace of f to the n acting on V t to the n. Now, for this talk, we'll just take this as a black box, but it isn't just a fact about vector spaces, and I mean, one proves it by induction on the dimension of the vector space. Now, let's use our friend, the Lefschetz formula. We know that the cardinality of fq to the n points in x0 which is equal to the cardinality of, well, let's call first x the base change of x0 to the algebraically closed field. So now we have a variety of an algebraically closed field as we need for the Lefschetz formula. Now it can be seen, but it's quite intuitive if you think about it, that the cardinality of fq to the n points in the variety x0 defined over fq is equal to the cardinality of points fixed by the phi to the n Frobenius in the variety over the algebraically closed fields. Because essentially the algebraically closed field, the algebraic closure of fq is just like the smallest algebraically closed field containing fq. So the properties of the Frobenius essentially do not change. And in particular, we have again the fact that in an algebraic extension, the fixed points by the nth power of the Frobenius are the points belonging to the nth power algebraic extension. Don't know if that is clear, but it's something that we have already said. Okay, let's apply Lefschetz, and these will be equal for the sum to the sum for I going from 0 to 2 times the dimension of minus 1 to the I, the trace of the nth power of the Frobenius acting on the ith étale cohomology group of X with coefficients in QL. Nice. Let's plug this in the formula. Or maybe let's not change the statement. Okay, let's plug it in the formula. And so t this with the t of the logarithm of z of x0 t will become equal to the sum over the n to this of the sum over the I of minus 1 to the I times the trace of phi to the n acting on the ith cohomology group. So phi to the I acting on the ith. No, wait. No, wait. It was right in here, sorry. Okay. Times t to the n. Now we change the finite sum with the infinite sum because we can. And this becomes the sum over I going from 0 to 2d of what? Of minus 1 to the I times essentially sum over L of the trace of the star to the n acting on hi t to the n. And this is the fact about vector space, the formula appearing in the fact about vector space I recalled you before. So this is just the sum over I of minus 1 to the I times t logarithmic derivative of the determinant of 1 minus the Frobenius of t acting on the ith cohomology, the minus 1. Then plug in the minus 1 to the I, change this sum with all the operations involved. We reach this formula z of x0 t equal to the product of the determinants of 1 minus a star t hi of x q to the L to the minus 1 to the I plus 1. And guess what? This is our PI. Well, this is a big deal. So, the theorem Deligne states, instead of the Riemann hypothesis, is that, well, probably I could have not erased everything, but given pi a priori depending on the variety, but also on L, on the prime L, we have that pi of x0, L is independent of L, well, has integral coefficients, independent of L, and has complex root of modulus q to the minus I over 2. This is, thanks to this factorization, the translation of the previous statement of the Riemann hypothesis. So a statement on étale cohomology. Okay, so we're ready for last mile. The first thing that Deligne does is to show that this assertion is in fact implied by this other theorem, which we will call again Riemann hypothesis. So it goes like this for all I and L different than the characteristic of
Recording in progress.
FQ. The eigenvalues. Oh, well, clearly the roots of these are the eigenvalues of this phi star. I mean, by definition of eigenvalue. So the fact that we are talking about the eigenvalues of phi star as a map from the ith cohomology group, the base change x with coefficients equal acting on itself is kind of obvious, are algebraic. And algebraic numbers. And all their complex conjugates have modulus q to the I over 2. Okay, I'm not going to prove this implication because it is rather technical, and I mean, to me, it does not really add anything, I don't know, spicy to the proof. It's just a technical change. Now, why did we choose étale cohomology apart from having these nice leftsets? Is that it has some properties that help us to rule out a lot of cases, where by cases I mean indexes I, and this is quite surprising. So let me first state an intermediate result. So let y to be x intersected h be an hyperplane section. Where h is the hyperplane. Then for all I bigger than or equal to 2, we have maps from the hi minus 2 cohomology group of y with coefficients in ql to the hi cohomology group of x with coefficients in ql, compatible with the Frobenius, such that for I equal to the dimension plus 1, this map is a surjection, and for I strictly bigger than this d plus 1, these maps are isomorphism. And this is essentially the key to the proof of Riemann hypothesis. To do a kind of induction on the dimension by considering first lower dimensional varieties, and then by using these kind of properties move upwards. Let's see the first example of this. As I told you, this example will rule out almost all the indexes of cohomology groups which we have to check. Proposition: the Riemann hypothesis restricted to this I equal D, so just consider this assertion where you check only I equal to the dimension of X. Implies the Riemann hypothesis for all I. Why? Poincare duality essentially tells us that the Riemann hypothesis for I equal to D minus, the index equal to 2D minus I, and the Riemann hypothesis for I equal to D are one implied by the other. Let's make an induction. Well, let's hint an induction on the dimension. So for the dimension of X equal to 0, one might imagine and in fact also check that the assertion is trivial. In the general case, what one does is, okay, we are dealing with a lower dimensional variety Y. So what we have is that the Riemann hypothesis, thanks to this theorem, the Riemann hypothesis on D minus 1 for the variety Y implies the Riemann hypothesis for D plus 1 of X, and so in particular by Poincare duality also that for D minus 1. By the very same result, the Riemann hypothesis for I of Y is equivalent to the Riemann hypothesis for I minus 2 of Y is equivalent to the Riemann hypothesis for I of X for I in this case would be bigger than D plus 1. So in fact, the only case that is excluded from these kind of implications from Y to X is the case X equal D. So if we assume the Riemann hypothesis for the index equal to the dimension of the variety, by this induction, we can prove the Riemann hypothesis for all the other indices. Finally, for us, the inequality I promised you. Is there any questions so far? Okay. If not, we state this assertion that we call smaller HD. It goes like this. For any smooth projective even dimensional variety x0, all eigenvalues of the Frobenius on H D X QL, where X is always the base change to the algebraically closed field, are algebraic. And this is like the same piece we have there. And if alpha is one of those, then alpha satisfies this inequality. Q to the d minus 1 halves smaller or equal than the absolute value of alpha, smaller or equal than q to the d plus 1 over 2. Proposition RH d for all d into n implies RH d for all d in n, which we already seen implies RH. How does one show this? Okay, so let x0 be, as always, of any dimension, in the sense that of dimension d, any natural number. Let alpha be an eigenvalue of the Frobenius. Now, by goodness, alpha to the k is an eigenvalue of the Frobenius acting on hkd of x to the k ql. Let me move to, well, let's see what is this like. Okay. So, in particular, this allows us, if we consider k even, then we have the algebraicity of alpha to the k, and so we have the algebraicity of alpha because it will be just a kth root of our friend. Assuming RH, smaller h, for dimension equal to k times d, so in particular we're assuming k even, we have that, q to the k d minus 1 divided by 2 is less than or equal to modulus of alpha to the k less than or equal to q to the k d plus 1 divided by 2, which means, well, just divide everything by k, q to the d over 2 minus 1 over 2k less than or equal to the absolute value of alpha less than or equal to the q to the d over 2 plus 1 over 2k. And by taking k going to plus infinity, we have that the absolute value of the modulus of alpha is a complex number. Sorry, I keep saying modulus. It's the absolute value of modulus is equal to q to the d divided by 2, which is Riemann hypothesis for dimension d. And this is as far as I wanted to bring you. For bibliography, well, you will have on the website more precise bibliography, but let me just say a couple words. The part regarding our elliptic curves is taken from Silverman's arithmetic theory of elliptic curves, if I'm not wrong. Well, Silverman's book on elliptic curves. The part about Riemann's hypothesis for varieties is, well, first of all, taken by Say's article, which is Conjectures de Weil. I do not know any French, but conjecture of Weil 1. Then the graphic you've seen is taken from this paper by Katz. And finally, the part about the introduction of étale cohomology, and also some parts of these proofs were taken by some notes by Kowalski about the proof of the Weil conjecture. Thank you.
Beautiful talk, Federico. Are there some questions? Not in the room. From home, online? Francesco?
No, any question?
That's all. Thanks again, Federico.